Hello. In this lecture, I'm going to discuss about photoconductive detectors. From now on, we are going to look at specific types of detectors. So I'm starting with the photoconductive detectors. As you know, photoconductive detectors are detectors in which the conduction itself depends on the input photon flux. That would mean that the resistance of such a device would actually change in presence uh, of the external photon flux. And that proportionality with the input flux and the corresponding change in the resistance is how the detection process happens. So in this lecture, uh, we are going to study the noise associated with this photoconductive process, look at microscopically what is going on with the charges and how exactly this process actually happens given the energetics of such a semiconductor device. So these are essentially semiconductor based detectors. And what you have is semiconductor crystals which have been doped with mercury, cadmium, tellurium, and so on. And by doping these dopants in various proportions, one can actually modulate the cutoff wavelength that these detectors can operate on. So photoconductive detectors are largely known for being operational at very long wavelengths, that is deep into infrared and so on. So for example, cadmium sulphide based detectors have been used for extremely long time, actually very early on, because the transition associated with the cadmium sulphide matches very well with the response of the human eye. So you see that, for example, detectors that, for example, spontaneously switch on street lights in the night, when the sun goes down. So that kind of a response would clearly match well with the human eye response, and hence one can automatically switch, a circuit like that. So, so there are various materials used, and I'm not going to really focus on the material characteristics per se, but depending on this choice of the semiconductor as well as the choice of the dopant, one can actually get a variety of wavelengths for this photoconductive detectors to operate. Right. So here is a schematic of what a photoconductor detector would look like. So what I have here in the blue is basically metal, and so is the blue on the other side. So what I have got here is actually a bias. There's a voltage V applied across this, and at the bottom I have a resistance, and I have amplified which might amplify the small changes that we have, and I have a meter that measures the voltage. All right, so what is happening here is uh, in presence of light, this particular yellow line, right, is actually the semiconductor crystal, the doped semiconductor crystal. Um, so what happens is that the resistance across this particular photoconductor material changes, and you see that these are in series, so the appropriate corresponding resistance changes in R, and that change is what is measured in the output. So this is clearly, it requires an external bias for such a detector to operate. Right. So what we have done here is the following. So, you see that there are these finger-like structures. So these are essentially called as the interdigitated gap. So idea is to maximize the surface area. You can clearly see that this will give me a large surface area comparison to maybe just a straight line. And one is also decreasing the distance between the two terminals, right? So as to decrease the loss of carriers that might be generated. So you see that the carriers are being generated within this yellow thin sample, if you like, and these carriers need to propagate to form a current from for example, from the positive to the negative. And you see these, if this material is significantly large, those carriers will be lost due to recombination, We will talk about this in little more detail, but the idea is should be clear that we want to make this material reasonably thin so as to not lose the carriers that have been generated as a photo response of this material. And clearly what happens is in presence of light and in absence of light, that's dark and light, the resistances typically drop off from few megaohms to few kilo ohms, right? And clearly the resistance within this photoconductive device is proportional to the input photon flux itself. Um, yeah, so that essentially how a typical detector works. But now let us look at the energetics of this problem. So the mercury doped, for example, germanium semiconductor detector is specific example that I am taking. So mercury here forms something like a acceptor level. It's a dopant, so it doesn't really form a band. It just forms a thin acceptor level within the band gap of the germanium semiconductor. So these two horizontal lines in blue is the original band gap of the bare germanium. And you see that roughly you have the band gap of a 0.75 EV, right? And then what you have here, the main process. So for example, once you dope mercury into this germanium crystal, you will see that what you create is basically this acceptor level, right? And so these acceptor levels are the ones, remember there is a lack of electron there. So these empty bins which I have created is typically the acceptor levels which are available. Now in germanium, uh, quite normally you also have some impurities of the donor kind. Okay, so there are very few of them. So these are donor levels are just below the conduction band, and you see this is a typical neutral donor atom which has electron which is sitting with it, excess electron, right? So you see this the situation when we dope mercury in germanium, it so happens that the acceptor levels are much larger than the donor level. So that is uh, uh, the main distribution of, for example, availability of states and so on, which is determined by this condition that the acceptors are much more than the donor atoms. All right, so the main process that happens is this, that when the photon comes in, this dotted in yellow captures the main process. And when the photon comes in, it basically releases an electron from the valence band of the germanium, and the electron makes a transition to one of these acceptor atoms, right? Because they can actually hold the electron. So you see that this now becomes such a acceptor level with an extra atom is now the ionized, you see, acceptor atom which has got an overall negative charge. So it is this electron that is now going to travel one way, and the corresponding hole is going to travel the other way, generating a current in this device, right? So you see that without the energy given by the photon, there would be no hole and no free electron to travel across. But you see, in presence of the light, there is a photo excitation of the electron from the valence band to the one of the acceptor levels. So you see that clearly there is a band gap, and this band gap is about 0.09 electron volt, which what gives us a cutoff wavelength of about 14 micrometers, right? So you need to have a photon which has got an energy larger than this band gap for this process to happen. And you see that the largest thing does happen at the band edge. So this forms the cutoff wavelength, or the minimum energy required for such a release of the electron. Now there are a variety of other processes that are happening, right? One thing can happen as this electron travels, it can recombine with another hole, right? And you see this is recombination. So you see both the entities that were creating the current are lost for the external circuit, and this recombination is going to be a biggest challenge for this process, right? The other thing which can happen is, because there are lot many acceptor, there's empty levels here, the donor atoms can happily give away their excess electron, and which can come back and occupy one of these. So you see, these empty states which were available for the electron to come from the valence band are now occupied. Hence this particular state cannot be really occupied by this by the hole. So the occupation of that electron, donor electron, in the acceptor levels is essentially limiting the whole current that is there in this photoconductive circuit, right? So these are the various, kind of summary of the various processes. I have tried to indicate each of them with appropriate symbols. For example, so once the donor atom loses the electron, it basically gets ionized. So this is an ionized donor atom, obviously with a positive charge. Similarly, this was the ionized acceptor atom with a negative charge, and this was the neutral acceptor atom. And so all the space below the EV is occupied by electrons of the germanium, and the whole current is the dominant current in this device. So there are some pros and there are some cons, right? So let's look at the pros. One thing here, it detects long wavelength photons. So one can actually come up with materials where it can detect all the way up to 50 micrometer, right? That is significantly large wavelength. One more thing very important is, like, for example, uh, in some of the other devices, like the devices based on photoelectric effect, you need to pull out the electron from the material itself. So the energy required for the electron to be pulled out is, needs to overcome the surface potential barrier, which might be significant, right? So there is no there is no release of the electron from the surface, so one doesn't require to overcome such large potential barrier, and that is again the reason why one can actually detect this long wavelength photons. Now there are problems. The One of the biggest problems is that clearly you can see that these wavelengths are in the infrared, and hence uh, the impinging photon flux and the thermal temperature of the device, the photons associated with the thermal vibrations are going to compete with this external photons which you want to detect, right? Because they are of similar wavelengths and energies. So you see, if we want to do a good job of this, one needs to actually, cool these detectors so that the noise due to thermal photons does not overpower the signal which is coming from photoexcitation of infrared photons which are coming. One of the significant limitations arises because of the carrier recombination. That is, you have the hole going along, but the electron from either the excess electron coming either from the donor, which is there in the acceptor level, can recombine to destroy the hole, or the electron that you had excited from the germanium itself can recombine with another hole, and so on. So you see that this carrier recombination basically destroys the current, the photocurrent that you have generated, right? So now you see there is an inherent randomness in this process. So the randomness comes about, because of this recombination. Like, clearly, this is the kind that we looked at for short noise, right? The electron is released, but then you see there is the scattering event, or reaching the end of the terminal essentially destroys or finishes the particular event, and there is a variation in this in the time that it requires to reach the other side, which is same as the variation, the distribution of times which might be there on an average for recombination and so on. So it is akin to short noise, right? We can clearly recognize that. And typically, so we will construct this argument carefully. Typically, the photoexcited carriers last for an average of, let's say, tau seconds before they are captured. So you see that, so for example, the photo conducting block of semiconductor is of certain length, right? So there is a certain time required for the electron to go from one end to the other end to contribute to current in the external circuit, right? So if the electron is lost midway, we sort of lose the current. So you see that the effective charge that contributes to external current is basically this ratio of tau over tau d, right? Tau d being the drift time required for the electron to cross the whole sample, right? So not everybody makes it through, right? The ones that do not make it through and are basically lost at for a are captured at a time tau before they reach the other end. So you see that only that fraction is the one that contributes to the current in the external circuit. So let's keep that in mind, and let's now go ahead and identify the basic processes, and from there we will identify our basic event, right? So I'm just putting everything in essentially black and white. That is your incident photon power, which is the number of photons per unit time, right? And the energy per photon, so it is h nu times the number of photons per unit time. There is a quantum efficiency associated with the detector, which is telling you that you know uh, for every photon input, what is the uh, do you generate a charge, right? So that process is for essentially it's a ratio of the number of charges generated divided by the number of input photon flux, right? So a number of photons coming in and the chance that you will generate a charge. So you see that this number is essentially from 0 to 1, if you like, right? When you say 100% quantum efficiency, what you mean is that for every photon input, you will generate a charge that will essentially be contributing to the current, right? So clearly you can see that the rate at which the carriers are being generated, right, it is simply this quantum efficiency multiplied by the incident photon power, and I have just divided by h nu to get rid of the energy business. So this is simply giving me a rate, right, essentially, which is per unit time, right? Where P now contains the number of photons, and uh, eta times P is gives me the number of charges that have managed to be generated, right? And h nu just gets rid of the energy which was just contained in the power. There is also, of course, the recombination loss. That's our major contribution, which is simply the number of carriers that you have divided by T naught, right? Because T naught is the average time it the process lasts before recombination happens, right? That's my sort of average time. So if you look at the carrier dynamics, you can see this nice rate equation that basically governs the carrier dynamics. You're looking at the rate of change of the number of carriers in time is basically the generation minus the recombination, right? That's all it is. So in steady state, of course, if I have the photon flux to be constant, then I generate my carrier dynamics is going to remain a constant, right? That would mean that essentially this dnc over dt is equal to 0, and thus you see that the number of carriers generated is basically proportional to the time lifetime of the recombination time that is there, right? So number of carriers, of course, is proportional to the power input. It is certainly proportional to the quantum efficiency. It is also proportional to the time or the lifetime uh, of the carrier generated before it gets lost. All right. Now let us look at a singular event arising out of the current, which is composed of a single electron, right? It's a current pulse, if you like, containing just one electron. So that is simply the charge of that electron divided by the time required to go across the sample. So V bar here is basically the drift velocity, and D is the length of the semiconductor crystal across which the electrodes are kept, right? That's my external circuit. So the electrodes and the semiconductor material in between form that length D, which the electron needs to travel maximum. That's a maximum distance electron needs to travel to create a current in the external circuit, right? And the other thing which we know, which I have not dealt with too much, but you see there is this notion of mobility. So the drift velocity is actually proportional to the electric field which is present, right? And mu is a parameter called mobility, which is a characteristic of this material, right? So you see that greater the external bias, greater is the electric field, and hence greater is the drift velocity, and more will be the current, if you like, uh, because the time required for the electron to go across is going to be small, right? So the total current is simply the current due to the single electron times the number of carriers that we have, right? And that we have already got here. So one can rewrite this clearly in this following form, that my total average current is simply charge times the quantum efficiency by h nu, right? That was coming from our generation rate itself, and T naught by Td now clearly comes out as the proportion of the charge carriers that make it as current times the power, which is the power in the input photons, right? So this we have got, and this really supports my statement which I had made earlier, that it's only this fraction that contributes, you know to the current in the external circuit. So there is a drift time. This is a specific time required given the particular bias. There is going to be a certain drift velocity associated, and one is comparing that with the lifetime of the electron before it is lost due to recombination, right? So that essentially is a important this is an important relationship that we will come back to again when we look at the short noise. Right. So to get to noise characteristics, right, like always, we need to identify the basic event, right? So the basic event is this single electron current due to a single electron going across, right? So there's a charge, there is V bar by D, and of course this current contributes only within the time 0 to tau, right? Before it gets lost due to scattering, right? So, and V bar is my drift velocity, right? So there you have. Drift velocity is fixed because I am putting my external bias is fixed. So it is only tau that remains as my major parameter that I need to carefully average about. So let's look at the Fourier transform of this particular uh, single event that we have identified, right? And this is going to be a function of certainly omega, because it's a Fourier transform in the frequency space, and it's going to be a function of tau. Tau is that parameter that tells me that that is when this particular event is lost. Like I said, because of one of those recombination scattering events. So this can be written down in this fashion. I'm not making any approximations on omega and t and so on. So you see, you will get a form of this kind, right? Clearly, the Fourier transform contains, the time required for the electron to go across, right? E by 2 pi is that factor, and this is simply coming out from the exponential part which is there, right? So if I'm looking at the square of this, I need to multiply this with its complex conjugate, and this is the form that I get, right? So now let's see what happens. So now that I have got my current mod square, this is what will go into my spectral density function. But you see, I have got this parameter tau still hanging around. I need to average over tau over the collisional statistics with the scattering events, which is destroying or leading to recombination of the charge or the loss of charge. So I can talk of again the same distribution g of tau that arises from the statistics of collisions. And if 1 over tau naught gives me the rate of collision, where tau naught is my typical the average lifetime of the charge before it recombines, then clearly the same arguments, g of tau d tau gives me the probability of collision happening between tau and tau plus d tau. The distribution looks of this kind. It of course is normalized, hence it's a distribution, and the average of the time required for the average time is indeed tau naught, as I mentioned, right? Because this is like the the first moment of it, which is you just calculating that, and that gives you the average, right? So on averaging, what I would get is this I omega square. Now this bar refers to averages being done over this the time scale of collision, right? This tau. uh, so I have done this multiplied by g of tau, and what I get is basically a form like this. So now remember that almost everything else, E square, V bar square, D square, and 1 plus omega square tau naught square was already arising out of the I omega tau. It's this tau naught square that has slipped in because of this excess because of what we have now done. Right. So now let's see. Once you have got this expression for the Fourier transform mod square, then we need to put it back into our spectral density function, right? So spectral density function clearly requires for me to consider the average rate at which this particular event is happening. So this is essentially the average rate of carrier generation, right? And we know that this average rate of carrier generation is got to do with E times n bar, if I like. So n bar is the rate at which carriers are being generated. E is giving me the charge that would have given me a current, but you see that not all of them contribute. It is the fraction tau naught by tau d is the one that contributes to the average current, right? So keeping that in mind, you see, I can rewrite my spectral uh, density function in the following form. So you have, so these what you, there was a 2 here, there is a 4 pi square hanging around there that takes care of this 8 pi square, and what you were left is a factor of 4 here, and there is n bar e square. The tau naught by tau d is coming from both the original thing, right? And you see that I can pick out one of these fractions, e times tau naught by tau d, right? And put it together with n bar, and I can replace that with my average current, right? This is what we have already seen. So you see that clearly my this is the essentially the basic result of carrier generation recombination noise for the photoconductive device. Clearly the noise is short noise kind. It has, of course, a frequency dependence, but more importantly, it depends on this DC current, average current that is flowing through. And this feature tau naught by tau d is indeed new, because that tells me the loss of this singular discrete events, which is happening at a scale of tau naught, even though it requires tau d time to contribute to a current, right? So this is one of my basic results of the recombination noise that we generate in this photoconductive devices. Right. So now let's say I want to do certainly better than this, in the sense that you see clearly as I increase my current, my average current, you see that my noise due to the short noise due to this recombination generation noise is going to increase. So if I want to do better than this, there is a neat technique that allows me to basically operate this device at essentially extremely at the limit of quantum mechanics. So we'll essentially get something called a quantum limited noise, in the sense that we are looking at fundamental, you know, the fundamental aspects like the energy, the quantum efficiency, being the only processes that determine my noise. In a sense, I have beaten everything other, like the average current and so on and so forth, which of course is proportional to the noise that is generated, right? So what is the way to beat this noise? And so this heterodyne detection, which is what I'm going to discuss now, is one of the ways which is used not only with photoconductive detectors but also in photomultiplier tubes. You name the detector, such a scheme can be utilized to basically beat the uh, noise that is coming into these detectors. Right. So let me first explain to you what the heterodyne business is. So what you do is, this is the detector which I am interested in. I got a signal that is coming in, and typically the signal is weak, right? And to detect this weak signal, what I do is this is the intensity of light that is coming in my signal. I mix up this signal with another bright source of light. Why I'm saying bright is because the amplitude of this wave, electromagnetic wave, which I'm impinging, is much larger than the typical signal. Signal is weak. So I impinge this, and then what I'm measuring at the detector is actually a collection of both the signal and this local uh, signal which I have put in. Okay, I'm this local extra uh, electromagnetic wave that I'm impinging is basically called a local oscillator. Now I'll tell you what is the meaning of heterodyne here. Heterodyne implies that there is a amplitude of the signal, and there is also frequency at which the signal is coming in, right? This is optical frequency. But what I'm doing is I am mixing this with another signal that is not really exactly same as my original signal, but it is slightly shifted from it. I've got, for example, a frequency which is slightly, this omega is a small, uh, has a small value, and it is slightly different, you know, such a way that omega plus omega s is slightly different from omega s itself, right? There is this small shift. That is why this is called heterodyne. You are beating the original signal with a frequency shifted signal. There are also techniques like homodyne, wherein this local oscillator has an amplitude which is indeed large, but it has a frequency that is exactly matching with the signal. That is called a homodyne detection. But what I'm describing here is a heterodyne detection. That is, the frequency is different slightly depending on what you want. It's in your control. The most important aspect here to govern, or to basically to keep in mind, is that the local oscillator has to be extremely steady, in the sense that my es is a fixed constant, my omega plus omega s is a constant, right? If you look at, there are no phase drifts of this. There might be phase variation that might happen in a signal, but there is no phase drifts or phase variation happening from the local oscillator. It's like a clock, which is simply ticking exactly periodically. So we will find that the detector output current is actually proportional to both the signal and the local oscillator. And let's see how we can beat the limits arising out of, the usual limits arising out of short noise, using this business of heterodyne detection. So here we have the signal Es of t, which is simply the amplitude of the signal times the frequency at which the signal is coming, and you have this EL, which is the local oscillator signal, right? Which is, by the way, that is being combined at a beam splitter, which sort of partially reflects and partially transmits the signal and the local oscillator into the detector. So you have essentially a frequency shifted local oscillator, which is stable. It doesn't drift in both in phase and as well as in amplitude, and the amplitude of the local oscillator is much larger than the signal amplitude. So now if you look at the total, the field, total signal at the detector, we are looking again, at the complex notation. You have the the ES, which is at exponential minus exponential I omega st. You have the EL, and you combine these two, and that is your V. So if you look at now the carrier generation, as we know, this is a square law detector. This is simply V times V star, and I'm saying that the carrier generation is proportional to this mod V square. So, and it is equal to a unknown constant, let me call it A, I will fix it later, times mod Vt square, right? So that is going to be my rate at which the carriers are being generated. So now if you look at the governing equations for the carrier generation, what you have here is dnc over dt, that's my rate equation. On this is my first term, which is the generation term, which is proportional to mod v square, and minus the loss term, which is nc by tau naught. Remember, tau naught was the average carrier lifetime. So we have done all that averaging and all that, so we are putting in here tau naught. So what I do is the following. I assume a particular solution of this above equation. This is the ansatz, right? It has got a DC component, which doesn't change in time, and the variation, if any, is in the N1 of t, right, which is the AC component. So you see that now let's be careful of the frequencies that we are using. Omega s was the frequency of the signal. Omega plus omega s is the frequency of the local oscillator. So this omega here is basically the difference frequency between the local oscillator and the signal, right? So this is precisely how I'm assuming the solution of this equation is. So it's got a DC component and it has got an AC component. This is what I do. So I take this ansatz and I take this equation. I basically insert these answers on the left hand side as well as on the right hand side, right? And you see that what I would get now is basically, the derivative on the left hand side will give me the dn naught over dt is 0, but it gives me basically I omega popping out of these, right? This is on the left hand side. Then on the right hand side, I have got essentially, the V and V star, remember they contain the signals. So I guess essentially these two terms. Remember, the first term is simply the mod square, and the second term is the cross terms that they might be once you multiply, the real parts, once you do this V times V star, right? There's of course this parameter A, which we don't know, and then on the last term you have this minus n naught over tau naught and n1 over tau naught, and you have this term. Now you see I've got this equation which has got terms which are varying at omega. So exponential I omega t and exponential minus I omega t, these are variations at omega, the difference frequency, remember, and it has got some coefficients. Similarly, there are coefficients which are at DC, right? So for example, n naught by tau naught has no variation in time. Similarly, this first term here, which is just the mod squares of ES mod square and EL mod square, these do not have variation time. So I can basically identify, the the what is n naught, and I can basically identify what is n1. So I put all the n1s on one side, take all the, and then compare uh, frequency by frequency terms, and essentially what I would get is this would become my new sort of n naught, and this will become my n1 times exponential I omega t plus its complex conjugate. So this is, I would request you to do this, exercise yourself. Please do it, and then you can obtain this particular form as the solution of this equation. Now, clearly, you see, whenever we look at these cross products, you see that the omega s gets cancelled, and what you get is the difference frequency, right? So this is my uh, current which is generated in my photoconductive circuit, right? Now I should realize that through my sample, the current is what? It is simply the number of carriers generated multiplied by E times V bar by D, which basically gives me 1 over TD, which is the drift time required to go across, right? That is my current through the sample. So what I do is basically implement this, and here I have got the current as a function of time, right? It has got so you see that there is going to be there's a DC part to this, right? Right, which is here, and there is also going to be an AC part to this, which is there, and we have combined it all together and put it in this manner to give us the time dependent current which I have. Now clearly, again, remember that I do not know A, right? And I have combined this, exponential I omega t part and its complex conjugate here. Remember, there is a 1 plus I omega tau naught at the bottom, and for the complex conjugate term, there will be 1 minus I omega tau naught. So I can fix this and put it up as a, as a phase, right? And I can write it down as this real quantity, because after all, it's a combination of two complex numbers which are complex conjugate of each other. So I can write it down this in the real form with an appropriate phase. So the phase is simply the tan inverse of omega by omega times tau naught. That's the phase, right? Now recall another thing, that my average current I bar is simply this factor. Remember, we had derived this, the DC current part for a constant input power. You would get this as my as the DC current. So what we do is the following. See, we can set the signal to 0, right? That would mean that my this time dependent part has gone to 0. That will basically give me something which is basically a DC current. So what I'm doing is comparing this DC current, right? Because I've set my signal to 0, my time dependence has gone away. I'm comparing this DC current with this, with this expression that I had already got for the DC current in a photoconductor circuit, right? So you will clearly see that I can identify this A to be precisely eta over h nu. The quantum efficiency, right? Eta being the quantum efficiency, which is the number of carrier generated per photon, and h nu being the signal at which this the h nu being the energy of the photon. By the way, this energy of the photon is precisely nu s, right? Omega s by 2 pi. This was the frequency of the signal, right? Which is nearly the frequency of the local oscillator as well. So there is no question about that. Remember, omega, the difference frequency is much smaller than the optical frequency. So what we have is I'm simply rewriting these in, remember that my EA mod EA square and PS are related. So I'm simply rewriting this in terms of the power in the signal, the power in the local oscillator, and so on and so forth, right? And I will set basically the DC part is going to be just this, right? Because I have set my signal to be 0, and you see that um, if I keep my my DC part, so you see that my signal is much smaller than my local oscillator. So I can do this, right? This is my DC part of the signal, and my AC part of the signal is simply, this other mixed term, which has got the cosine omega t dependence. So that square, the ES times EL is simply square root PSPL, right? And this is all real, so I can rewrite this in this fashion. So what I do is this: I got a current now which is got a time variation, but the variation is precisely at the difference frequency. It is far removed from the DC part. And I got the DC part of the signal as well. I really don't have to worry too much about it. It is there. So if I now look at this AC part of the signal, I can use a bandpass filter and filter out through my electronics connected to my photodetector a signal which is centered at basically omega, which is different. So I'm basically chopping away or putting away the DC contribution to the current. I'm just looking at this AC variation at the difference frequency. So this bandpass filters allows us to isolate and measure the signal about this difference frequency omega. So you see, I can now correspondingly look at the associated spectral density function, which is uh, centered at this difference frequency, which is precisely 8 pi square n bar times this. Now I just put in everything that I already know. My in this, so you see, I can clearly I can identify various things. This expression I had already got, right? And remember, I bar here is simply as given in this, which is my DC part of the signal, right? Which is this expression. And this would be the associated short noise, right? Recombination short noise, which is my largest contribution. Why is it my largest contribution? Because you see, this is clearly proportional to the power in the local oscillator, which is a very, very dominant term. So when this PL is very large, you see, I can basically neglect PS. So this becomes my dominant noise term. Right? Now let's look at what my signal is. Now remember, my signal is simply IS square, right? Which was this expression which I had written in the previous slide, square of it. And remember, there was a cosine omega t minus phi, but I have to now look at cosine square omega t, and I need to average this over some time. So that averaging of cosine square gives me a factor of half. And you see that essentially, if I'm looking at the signal to noise ratio, the noise is dominated by my DC noise, right? This is the expression that I have. Remember, I have said that PL is much larger than PS, so I neglected PS. You see, clearly you would see that every term in this uh, perfectly gets cancelled. Lots of terms. So for example, you see all that remains at the end, right? The PL gets cancelled, which is my largest contribution to the noise. So PL on the denominator, PL at the top, right? So only the PS is left, right? There is a eta square here coming from the square, and there is a eta here, so there's a eta left. There is a h nu square on the top. There is one h nu here, so there's h nu left, and there is a delta nu which is sitting here. Every other term essentially gets cancelled in the signal to noise ratio. So which is amazing, because you see, what we have done is the signal to noise ratio has become independent of the local oscillator, even though, so it is simply used as a trick to basically beat my original signal with this local oscillator, which has got significant amount of power and energy. But we have to make sure that that power is a constant, there is no phase variation and so on there. And if you make PL large enough, then you see that the dominant noise comes about largely from that short noise coming from PL, from that power, right? And that is what gets cancelled with my signal largely to give me something which is now directly proportional. The signal to noise ratio is directly proportional to only the power in the signal. This is an amazing result. So let us say that I can make out a signal that is equivalent to the noise. That is, if I set my signal to noise ratio to 1, then you see that the minimum power which I can detect is basically dependent on something very quantum mechanical. It is the energy per photon, it is the bandwidth, of course, and it is inverse of the uh, quantum efficiency. So larger the quantum efficiency, smaller is the power which I can detect, right? It is simply limited by these extremely fundamental constituents of my system. It is just basically depends on the energy of the photon, right? It's in single photon, and it's depending on quantum efficiency, and there is this little factor of 2, but this is the quantum limit of optical detection when I do heterodyne with, in this case, the photoconductive circuit. I can do heterodyne with the uh, you know photo emission circuit, like in a uh, photoelectric effect, like in a PMT. But this is just the discussion on how this business of heterodyne really works when I use a optical detector. Right? It's a very, very powerful technique to basically, beat the noise and to basically focus on the very fundamental aspects of my input signal, the very quantum nature of it, which is the energy carried per photon, the intrinsic quantum efficiency of that detector, and nothing else.